Hi, good morning, everyone. It's a great pleasure I can present my work in this conference. My name is Liangliang. Topic I'm going to present today is IgM detection using long-period fiber grating sensor. First, allow me to introduce myself. I'm the PhD student from the optics and the photonics group at the University of Nottingham. My supervisors are Dr. Serhiy Korposh, Dr. Ricardo Correia, and Professor Steve Morgans. Our research interests are applying the optical fiber sensor for the physiological monitoring, for example, to monitor the heart rate, the skin blood oxygen saturation, and the blood pressures. We do the grating-based sensor for the physical parameter measurement, such as the temperature, contact pressure, and the refractive index measurement. We also develop optical fiber-based gas sensors, the ammonia and carbon dioxide for the environmental and the healthcare applications. So in this presentation, I'm going to start with the introduction of the long-period fiber grating sensor, give you a brief idea of what is LPG sensor and what it does, and then go through the fabrication process for the LPG sensor and LPG sensor surface modification, and demonstrate the LPG sensor we used for the detection of human IgMs, and on the end, make a conclusion. So there are plenty of advantages using optical fiber as the sensors. So most of them is well known and you're familiar with. I'm going to skip this part. So what is LPG sensors? So let's start from the optical fibers. As we know, the optical fiber is highly efficient waveguide for the light propagations. So the light is normally trapped and propagates inside of fiber core due to the total internal reflection, the higher refractive index in the core compared with the gratings, compared with the cladding. LPG sensor is made by inscribing periodical gratings inside of the fiber cores. So when the light propagates through the gratings, some part of light will be coupled into the claddings and lost from the fibers. So the light propagation mode will be altered from the fundamental core mode into the core cladding core propagation mode. So that part of light that has been coupled into the claddings are wavelength dependent. They are defined by the grating period, which is the distance between the two adjacent grating plates, and the effective refractive index of the core, and the effective refractive index of the claddings. So this is the setup we use to fabricate the LPG sensors. So as you can see, the setup is quite straightforward. And what do we have? We have the classical YAG laser, which will generate ultraviolet laser with a wavelength of 266 nanometers. So the UV laser is going to pass through a cylinder lens and an amplitude mask and project a periodical UV light pattern on the optical fibers. The optical fiber we used is photosensitive, so under the UV exposure, the refractive index of the fiberglass will be changed. So that's going to produce a periodical refractive index profile inside of the fiber cores. So that is the LPG sensor. So the laser system we used is quite robust. It takes about 15 minutes to fabricate a typical 3 centimeters length of LPG sensor. It has good fabrication repeatabilities, can fabricate the sensors with different grating periods, including the fabrication of the fiber bracket gratings. So LPG setup, LPG basically detects the refractive index based on the either the wavelength shift or the intensity changes. For a traditional wavelength shift based LPG sensor, usually a spectrometer or the interrogator is required to trace the shift of the wavelength. So that's going to raise the total cost for the setup about 5,000 pounds. But however, what we can do is we can fabricate the intensity-based LPGs replacing that light source and spectrometer with a single LED and photodiode, detect the intensity change of a single wavelength. So by doing that, the LPG setup can be miniaturized, and the total cost for the setup can be as low as £100. So the human immunoglobulin M is an important antibody in our body fluids. So it is the first antibody produced by our immune system in the course of the infections. So the level of IgM in the blood serum can be used to screening the selective IgM deficiency, can be used to indicate the neonatal infections, and can be used to help diagnose the dengue infections. So in order to detect the IgM, we initially coated the optical fiber LPG sensors with the silicon nanoparticles via layer-by-layer techniques. So the LPG surface was initially hydroxylated by using the KOH solutions in order to have the negatively charged surface. Then we ultimately deposit the positively charged polymer PAH and negatively charged silicon nanoparticles. So the negatively charged silicon nanoparticles in the solution will self-assemble on the positively charged polymers by the electrostatic force. So after repeating the coating process for the 3 layers, which is optimal layers has been confirmed by our previous studies, we decorate the silicon nanoparticles with even small size of gold nanoparticles to form shell structures. The reason we use the silicon and gold nanoparticles is because it has a large surface to volume ratios. It can essentially create more of the contact surface and creating more of the binding sites on the sensors. So the gold nanoparticles can enhance the electric field and increase the sensitivities. So the SEM images on the below just show the successful deposition of the silicon nanoparticles on the optical fiber surface. This is the optical fiber. There's some nanoparticles, silicon nanoparticles coated on the surface. The LPG sensor can monitor the layer deposition process. As each layer deposits, the refractive index of the LPG sensor is stably increased. So as a result of changing the Copley condition, the LPG sensor shows a wavelength shift and the intensity change in corresponding to each layer deposit. So the TM images here just confirm the gold shell structure on the surface of the silicon nanoparticles. So furthermore, we use the chemical linker to conjugate the anti-IgM on the surface of the LPG sensor. So there are more details about these linkers you can find in your paper. So the anti-IgM is the specific binding site for capture the human IgMs. So the sensing principle of such sensor is it detects the refractive index change after the binding of the IgMs. So the specificity is relies on the sensing film and the choice of the bioreceptor. What else we have done later on to improve the specificity is we tried to use the BSA, which is the albumin, to block the potential unspecific binding sites before we do the measurement. The one advantage of using LPG-based sensor is it can dynamically monitor the binding process. Here I'm showing you a group of results we did using the prepared sensor to detect the IgM in the aqueous buffer solution. As you can see, compared with the blank sample test, LPG shows a wavelength shift in corresponding to the binding in the different concentration of the solution. So the sensitivity after doing the calculation is about 11 nanometers per nanogram per millimeter squared. And the limit of detection is about 0.02 nanogram per millimeter squared. Here I'm showing the dynamic binding process is captured by the LPG sensor. as you can see, in the first 7 to 8 minutes, the signal is gradually increased as indicating the continuously binding of the IgM on the sensors. So the sensor has a fast response time at less than 10 minutes, which is it's good compared with the traditional ELISA-based method. And it can detect the IgM in the solution without the requirement of the additional labeling. So in summary, the LPG sensor we proposed is a small size and is capable of making cheap and portable devices. So it's a label-free detection of IgM in the solutions. It can monitor the binding process of the proteins, and it's suitable for the binding kinetic studies. In the end, I would like to thank you all for your listening and thank you for our support from the University of Nottingham, the University of Kitakyushu, and my sponsors, EPSRC. Thank you very much.